Let's take a moment to recall the chain rule for functions of one variable, although perhaps not the way you originally saw it. So if y is a function of x, and then x is a function of t, we could write this in this diagrammic way. So y is dependent on x, and x is dependent on t. And then for each branch here, right, we have the variation of y with respect to x, or the variation of x with respect to t. So then if I want to know, if I want to go from the beginning all the way to the end, what's dy dt? Well, it's the product of those two, dy dx and dx dt. And the reason we like this notation is that it suggests that the dx's cancel out. Now with multiple variables, it gets more complicated, but we can use similar ideas. So let's start with a scenario where z depends on both x and y, and then each of those variables depends on t. Now along each branch of dependency here, we have a derivative. So z depends on two things, so that means we need to use partial derivatives when it comes to z. Meanwhile, x only depends on one thing, so I can use the ordinary derivative for that. Y depends on only one thing, so I can use an ordinary derivative for that. So ultimately here, z only depends on t, so that means I can write an ordinary derivative of z with respect to t. But to get there, I have to use partial derivatives. So z depends on x and y directly, and I take the product of the two derivative terms along the top branch from z to t. And then I have another way of getting from z to t through the bottom branch, so I also have the product of those two derivatives. So that's the chain rule for this situation. Let's look at another scenario. Let's suppose that y depends directly on a variable s, and then s depends on two variables, u and v. Okay, y depends on only one thing, so I can write an ordinary derivative. But s depends on two things, so I have to write partial derivatives for s. Y ultimately depends on two variables, u and v, so I have to talk about partial derivatives of y with respect to u and v. So the first one of these, okay, I only have one path from y to u, so I multiply together the terms that I find on that path. And if I want to know the derivative of y with respect to v, again, I only have one path from y to v, so I multiply what I find along that path. So that's the chain rule for that scenario. So as you can see, because we have so many variables around, I can't say that there is one chain rule. Instead, it's a process. All right, and the process goes like this. You draw these dependency trees, right? And then you follow each path for a dependent-independent pair. So what I mean by that is, before I said z was independent, I'm sorry, z was the dependent variable, t was the independent variable, so follow paths from z to t. Or here y was the dependent variable, and u and v were the independent variables, so I had to follow paths for each of those. So you follow each path, multiplying the derivatives together as you go. And these trees can be as deep as you like or as long as you like. And then you add up over all possible paths for that pair. So again, we had two paths to get from z to t up here, so I added together two terms. Here I only had one path from y to each of the independent variables, so there's no addition, there's just one term in each of those.